Okay, so what can I do for you? Questions? Floor is open.
Hi, Professor. Yes, from number 30, I was trying to do the homework. This is session 1.5, question number 2 and 3. I didn't understand the question well. Can you go over that question?
Section 1.5.
Yes.
Okay. Sure. So section 1.5, number 1 is to,
One, no, Professor. I knew how to do one. Is 2 or 3?
number 2.
Mhm.
Okay. So we let n be equal to the number 210. Prove that n minus p is prime for every prime p such that n over 2 less than p less than n. So you can think of the following picture. Here you have the integers from 1 up to n. In this case, n is 210. N over 2 is half of that. That's 105. And what this says is, if you find any prime p in this interval, right? If this is prime, then n minus p, or 210 minus p, is also going to be prime. So to do this, you have to find all the primes between 105 and 210. So that takes a little bit of work, but that was problem 1. In problem 1, you use the sieve of Eratosthenes to find the primes in this interval.
Mhm.
So take each of those primes and calculate, for example, do you have such a list? I don't know.
Yes, I do.
Okay, so give me a prime in this interval.
107.
Okay, so if p is 107, n minus p is 210 minus 107, which is 103, and this is also prime.
Yes.
And for every prime in this interval, you're supposed to just check or show that n minus p is a different prime. So for every prime between 105 and 210, there's a prime between 1 and 105. So this is just a calculation.
Okay.
Now,
So
you could also use Maple to do this if you could write a little Maple program, but it's not that hard to do it by hand either, but it does take a bit of time.
so Professor, because it's a proof, so all we have to do is like to calculate all of that, because n minus p will be like q in the problem, because it's a prime number q less than n over 2. So it's just like calculating, like finding all the q's.
So
we have to
the
do
second
like
part of the
something.
problem, you have to show that there's some other prime q which is not of this form. So for the second part is to find a prime q such that q is between 1 and 105, but n minus q, which is 210 minus q, is not prime, is composite. So this is just doing some work by hand, some calculations.
Okay, so we don't have to do like anything abstract in this kind of problem, right?
Yeah, this is
It's like
just
computation.
computational. This is,
Okay,
yes.
because sometimes the word proof like make me confused, like, okay, so should we look like only computing like some problems here, or
Well,
should we
I
do
mean,
abstract
prove-
things?
Prove means give an argument to show a certain statement is true. And a calculation can show that a certain statement is true, and that's fine. Sometimes
Okay.
proof is more abstract, sometimes it's more concrete or more computational or more numerical.
Okay. Let me ask you a quick question about number 3. So number 3 say show that n minus 2 to the n. So n will be like any integer from 0 to n. The exponential n.
For section 1.5, number 3, we take n to be 105 and 2 to the n to be a power of 2 greater than or equal to 2 and less than 105. So if 2 to the n is at least 2, that means n is at least 1. So n equals 0 doesn't satisfy this. And the highest power of 2 less than 105 is n equal to 6, I think, because 2 to the 6th is 64, and 2 to the 7th is 128. So you have to check these 6 cases. So you might have, so n equals 1, 2, 3, 4, 5, and 6. And 2 to the n is 2, 4, 8, 16, 32, and 64. And n minus 2 to the n, which is 105 minus 2 to the n. 105 minus 2 is
3.
103. 105 minus 4 is 101. 105 minus 9 minus 8 is 97, I think, and so forth. 105 minus 64 is 41. And so just check that these are all primes.
Okay. Okay. Thank you, Professor.
Sure.
Professor,
Yes.
quick question. For example, for the question number 1, I know that it's possible to do it by hand, but if we get the answer by using Maple, it's okay with you also?
Well, so the answer is the rule is always to solve the problem. So the problem says use the sieve of Eratosthenes. So for this problem, you have to use the sieve of Eratosthenes. And the purpose of the problem is to teach you the sieve of Eratosthenes.
So we have to do the table with the 210 numbers, right? And start
Correct.
crossing out numbers. Okay.
But of course, if you want, you can just use the odd numbers because except for 2, all the primes are odd. So you just have to write down the odd numbers. So that's only 105 numbers. So you
Okay.
cut the work in half.
Yeah, that's good. Okay, thank you, Professor.
Sure.
Professor, what I did for question 1 was like I put like all the numbers from 1 to 10, but I didn't write it like 5 times, just once, and say that we need to cross out like any multiple of the prime number 2, 3, 5, 7, 11, and 13, and cross it out, and that's it. Because then it was going to be like too much.
Well, it's up to you.
Okay.
But it's, it's, if you have the time and the big enough piece of paper, it's kind of fun to actually see how it works. But it's up to you. I like those kinds of problems.
Professor, let me ask you a question about the test. Like, how should we expect the question for the test? Like, they're going to be similar to the homework problems or the problem that you solve during the lectures? Because it's kind of confusing because there are many problem homework questions that are really hard to solve. And then that made me like a little bit nervous. Like, I don't know if we should expect the kind of question on the test.
Right. So the homework problems Well, the exam problems will be easier than the homework problems. Because for the homework problems, you have, you know, as much time as you want, but the exam is a standard 2-hour exam. So the exam questions will be much easier than the homework.
Okay, thank you.
Professor,
Yeah,
on the topic of exams, so the exam questions, are they gonna be more proof-based or more computational based?
be both.
Roger that.
You know, there'll be some of each, and I don't know exactly how many until I make up the test. You know, but
Professor, could we go over number 6 in that same section 1.5?
okay, so I mean, a classical problem in number theory is to find prime numbers. And so 2 to the k is obviously not prime, it's a power of 2. But the question is, classically, if you add 1 to that, that's an odd number, is this prime? So here you want to show that if this number is prime, then k itself has to be just a power of 2, 2 to the n. In that case, this prime is 2 to the 2 to the n plus 1, which is sometimes denoted capital F sub n. It's called a Fermat number. So for example, just to see that some of these numbers are primes, if you have n equals, even n equals 0, 2 to the 2 to the 0 plus 1 is 2 to the 1 plus 1 is 2 plus 1 is 3. If n is 1, 2 to the 2 to the 1 plus 1 is 2 squared plus 1, which is 4 plus 1, which is 5. If n is 2, 2 to the 2 squared plus 1 is 2 to the 4th plus 1 is 16 plus 1 is 17. These are all primes. If n equals 3, 2 to the 2 cubed plus 1 is 2 to the 8th plus 1. 2 to the 8th, I think, is 256, plus 1 is 257, and I think that is also a prime. And so there, before they had computers and everything had to be done by hand, there was the possibility that every number of this form was prime. But you could also show, and this is the problem, that if a power of 2 plus 1 is prime, this power k itself has to be a power of n. And to prove that, you need to know some factoring from high school algebra. So let's see, what is it that we're supposed to know? You know that x to the, what's a good letter? I don't know. X to the n minus 1 always factors. Right? So x to the n minus 1 always factors, but x to the n plus 1 doesn't always factor, but sometimes it does. If n is odd, say n is 2m plus 1. This is x to the 2m plus 1 plus 1. And for example, x cubed plus 1 is x plus 1 times x squared minus x plus 1. I think that's correct. Yeah. And x to the 5th plus 1 is x plus 1 times x to the 4th minus x cubed plus x squared minus x plus 1. These are odd powers. And x to the 7th plus 1 is x plus 1 times x to the 6th minus x to, these just alternate going down plus and minus. And in general, x to the 2m plus 1 is going to be x plus 1. And then just going down by 1, x to the 2m minus x to the 2m minus 1, x to the 2m minus 2, minus plus plus, minus x plus 1. There's always this factorization. Okay, any questions about this? So this sort of factorization rule is the basis of the problem. If you have any number x to an odd power, x to that odd power plus 1 factors. So in particular, if n is odd, 2 to the n plus 1, which is 2 to the 2 to the 2 to the n, sorry. Yeah, so 2 to the capital N, which is 2 to the n plus 1, this will factor into, this is just the same formula with x equal 2. 2 plus 1 times 2 to the 2m minus 2 to the 2m minus 1 minus 2 plus 1. This is factorization, and this number is 3, and this number is bigger than 1. So if n is odd, so n odd implies 2 to the n plus 1 is composite. Okay, any question about that? So conversely, if n is prime, then, sorry, if 2 to the n plus 1 is prime, then n, sorry, if n is, so if 2 to the n plus 1 is prime, then n is even. Because if n were composite, 2 to the n, if n were odd, 2 to the n plus 1 would be composite. So if 2 to the n plus 1 is not composite, that means prime, then n is even. So
you will always see nurses, and you will always see healthcare workers coming in with it. But to be honest,
any questions about this? Because this is the basic step, that this factorization rule says that if n is odd, 2 to the power n is composite. Or conversely, if 2 to the n plus 1 is prime, then n has to be even. So suppose 2 to the k plus 1 is prime. So then k has to be even. But not only is k even, suppose k has an odd factor. So 2 to the k plus 1 is prime. Suppose k is equal to, see, I don't know, a times b, where one of these, let's say b is odd. So suppose k has an odd factor b. Then 2 to the k plus 1 is 2 to the ab plus 1. 2 to the ab is 2 to the a raised to the power b plus 1. And this is just of the form x to the b plus 1, where x is 2 to the a. So this factors into 2 to the a plus 1 times something else. So if k is an integer which has an odd divisor, then 2 to the k plus 1 is composite. So if 2 to the k plus 1 is prime, then k has no odd divisor, which can only happen if k is a power of 2. And that's the argument for a proof. Okay. If 2 to the k plus 1 is prime, k cannot have an odd factor. If k had an odd factor, it was divided by an odd number greater than 1, this would be composite. And the only number that has no odd factor is a power of 2. That's the proof. Right? It's very quiet.
That's great. Is it
Any questions about that?
think what I think there is-
Yeah, could you explain from where you set x to the b plus 1 and then you did x is equal 2 to the a?
Right, it's not.
I understand that, but then after you kept going after that.
Okay, so
Specific spray that basically wipes off.
we have the following rule. Let me say this again. So if b is odd, I'm just changing the notation slightly now. If if k is odd, x to the k plus 1 factors. Right? So this is just a factorization formula, right? Just like, in the simplest case, x cubed plus 1, when k is 3, this is 2 minus x plus 1, right? So this factorization rule, it's just, that's what it is, right? Just like x cubed plus 1 factors like this, okay? So that's what we start with. Right? So is this okay? Yes or no?
Yes.
All right. So suppose, actually, I'm a bad choice of letters, but okay. Suppose I'm just going to write it down again with a different letter. So if L is odd, or let's say if B is odd, then x to the b plus 1 factors. Right? So if b is an odd exponent, this factors. So suppose 2 to the k plus 1, or consider 2 to the k plus 1, this integer, right? If k has an odd factor, an odd divisor, b, at least 3, that means k is a times b, right? And 2 to the k plus 1, k is a times b, that's 2 to the ab plus 1, right? And 2 to the ab is the same as 2 to the a raised to the power b plus 1. So you have to tell me if there's a question about this. Right? you're taking a power of 2, 2 to the k plus 1. And if k has an odd divisor, b, that is k factors into a times b, where b is an odd number, bigger than 1, at least 3.
Okay, I'm
And-
I'm tracking. I'm tracking.
So 2 to the k is 2 to the ab, but you know, just from the rules of exponents, 2 to the ab is 2 to the a raised to the power b. Right? So here k is ab, and a and b are both bigger than 1. In fact, b is at least 3. This is a factorization. And just by this rule, if you use this rule with x equal to 2 to the a, so this is x to the b plus 1, where x is equal to 2 to the a, so it factors x plus 1, x to the b minus 1 minus x plus 1, x plus 1, whatever, this is 2 to the a plus 1 and so forth. In any case, this is composite. If k has an odd factor b, 2 to the k plus 1 factors into a product of two numbers bigger than 1.
Got it.
Right? So if k has an odd divisor, 2 to the k plus 1 is composite. So the converse or the contrapositive says, if 2 to the k plus 1 is prime, then k has no odd divisor. But you can write every integer as a product of primes. If k has no odd divisor, it's not divisible by any odd prime. That means the only prime that can divide k is 2. So k has to be a power of 2.
Gotcha.
That's the proof. Right. So, I mean, these are all problems that, I mean, just takes 1 or 2 sentences to state the problem, but it takes a certain amount of concentration and time to come up with the proof on your own. Any other questions?
Professor, I just have a question like, this is for session, I think 2.1, question 10. So that question said, prove that a to the q is congruent to a most 6 for every integer a.
Right.
So for that question, what I kind of did was, so I wrote a to the q congruent to a most 6, and then I wrote a to the q minus a is congruent to 0 most 6. And then I made an argument like factoring out a to the q minus a, which is equal to a times a plus 1 times a minus 1. And since we have 3 consecutive integers, we know that this is divisible by 2 and 3. So for that reason, I conclude that a to the q is congruent to a most 6.
That is exactly correct.
Okay.
100% correct. Exactly right. That's very good.
I was also doing some research for this question, and I found something that is called Fermat's little theorem.
Yes.
So I found like for example, a to the p is congruent to a mod b. So like do we have to break down this problem, like for example, so if we have like a to the q minus a congruent, I mean a to the q congruent to a, and then say like mode 3?
No, you don't have, for this problem, no, you don't have to do that. What you did is fine.
Okay,
All right, I mean, we'll prove that Fermat's little theorem in a couple of weeks. It's section 2.5 in this chapter. But no, you know, I mean, what you did is perfect.
okay,
In fact, it's better because you use less technology. You just use thinking, which is good.
there's another question. This is the sensation, this is point 2, I mean question number 2, that we have to find the non-negative residue of 5 to the 22nd modulo 23.
Right.
So I know, for example, like if we have, let's say 24 to the 22, so we know that this will be like 1 modulo 23 to the 20, I mean 1 to the 22nd mode 23. But here, like we need to calculate 5 to the 22nd, and then we divide and we find like the remainder, or there is another way that we can do this question? Like,
Well, let's see. So we know that 5 squared is 25, right?
mhm,
Which is congruent to 2 mod 23. Right?
yeah.
So for example, 5 to the 4th, which is 5 squared squared, is congruent to 2 squared, is congruent to 4 mod 23. Right?
mhm.
So for example, 5 to the 8th, which is 5 to the 4th squared, would be the same as 4 squared, or 16 mod 23. Right? I'm just trying to get,
Like different power. Yeah, I see what are you doing.
okay. So let's see, what else? Well, what about 5 to the 10th? 5 to the 10th is 5 to the 2 plus 8. That's 5 squared times 5 to the 8. 5 squared is congruent to 2.
Mhm.
5 to the 8th is congruent to 16. So this is congruent to 32. And 32 is congruent to 9 mod 23, right?
Okay.
And we want to get up to 22. So 5 to the 20th is 5 to the 10 squared, is congruent to 9 squared, which is 81. Let's see, 46, 92, see, 23 times 4 is 92. So this is congruent to minus 11 mod 23, because 81 plus 11 is
I got 12,
92.
Professor.
What?
12. So 81 divided by 3. 23 times 3.
So 81 plus 11 is 92, and 92 is 4 times 23. So 81 is congruent to minus 11
Okay.
mod 23. Right? That is 81 congruent to minus 11 mod 23 means that 81 minus 11, which is 92, is divisible by 23. And in fact, it's 23 times 4. So 81 is congruent to minus 11 mod 23.
Yes.
And we're interested in 5 to the 22nd power. So that's 5 squared times 5 to the 20th. And 5 squared is congruent to 2. And 5 to the 20th is congruent to minus 11. So this is minus 22, which is the same as plus 1 mod 23. So that's the answer. 5 to the 22 is congruent to 1 mod 23. That's one way to do it. I mean, there are a million ways to do it. And in fact, if you know Fermat's little theorem, that says the answer is 1 right away. But this is without using Fermat's theorem, just a direct calculation that 5 to the 22nd is congruent to 1 mod 23.
Thank you, Professor.
I've recorded this, so I will post it on Blackboard if anyone wants to check again later. But anything else? If not, we will quit for the morning.
Thank you, Professor. Have a good morning.
Thank you, you too.
Thank you,
Bye all.
Professor.